So welcome everyone to our lab meeting. It's my great pleasure to introduce Professor Hervé Abdi, who is currently a full professor in the School of Brain and Behavior Science at the University of Texas at Dallas. He was a Fulbright scholar for Brown University and an Orias Institute of Advanced Study Fellow in Paris. His recent work is concerned with face and person perception, odor perception, and with computational modeling of these processes. He is also developing statistical technique and mainly technique like PLS regression, STATIS, multidimensional scaling, and other technique like discriminant analysis or discriminant correspondence analysis. He did a huge work in this area during this last, I would say, 35 years at least. And so we met years ago in Paris. So we know each other. I mean, more than I know his work during this last 25 years. I mean, and we met in Paris, and we developed a very interesting collaboration with Hervé and other colleagues in Paris, where we developed technique like looking at the functional connectivity of the brain and extracting some features, extracting some characteristics from the brain. So this is something that we are still collaborating in, and we hope that we are going to continue this way. So Hervé, it's really my great pleasure to have you today, and thank you very much for accepting giving this talk to the team. The talk is about meta with this cov-STATIS, or how to perform multivariate factor meta-analysis with some same on top. So thank you again, Hervé. So the floor is yours.
Oh, thank you, Habib, and thank you for such a nice introduction. You're right, I just realized we know each other for now quite some time. Oh, well. So but it's nice we still keep being young, and despite all the years that we've been working together around each other. So I just let me just, before we start talking, let me tell you it's a completely informal talk. So what I want you is that don't be shy. Anytime you have something to say or you want to add or something is not clear, just go ahead and just mention it, and then we can make a small detour and so on. So I'm sure that the title that is here probably feels a bit strange when you look at it. Oh, and it looks like, okay. And so let's start with a bit of prehistory and why we're going to talk about methods such as DisTATIS. Let's start by looking at the general idea there. Very often what we have some type of data that for which we don't have a simple variable. In general, we use a variable, it's just a column in some data matrix, and we want to do things on these columns to represent as best as we can that data. But in some cases, the data that we have are not a column, and they can be themselves data matrices. And that has been what we've been working on for now around 20, 30 years, is how can we develop methods that will work for data matrices in the same spirit as we have method to analyze a data table, let's say with using principal component analysis or correspondence analysis or related method. So we started working on that a bit more than 20 years ago, and just because several problems that were coming from different origin were something we were working on. So the first problem, for example, that we had was trying to analyze the mental space of experts as opposed to non-expert. So for example, we've got wine expert, professional people, and some of the work was done in France, in Burgundy, which is one of the places where Chardonnay has been cultivated for centuries. So now the problem that we had, and we were also talking with, let's say, musician, professional musician, as opposed to just amateur or people who have no clue. And what we realized there is that we needed to have very simple tasks, because as soon as we bring verbal material, experts look incredibly smarter, incredibly better than non-expert. But now with the question is that what happens if we can make the task as simple as possible in such a way that you don't need to use a verbal approach to provide information. So what we found was if you look at faces, one thing that is a catastrophe and does not work is to do pairwise comparison of the faces and ask people to rate the similarity. Why? Because, well, the number of pairs is equivalent to n times n minus 1 divided by 2. So that meant that even with just 10 faces, we have 45 comparisons to do. And if we want to have some repetition, that means we can end up very, very easily having a couple of hundred to do that. And if you try once to do those type of tasks, you are going to find that this is absolutely horrible. So we just decided that we could not have that rating similarity will not work. So what can we get? We just realized that the simple thing was just to ask people to put together the faces that they thought were looking the same, and to put in different stacks faces that they thought were different. It's simple. Everybody can do that. Even children can do that when they're 2 or 3 years old. So that's a great one. But now the problem is that the data matrix for one participant will be a table with 0 and 1s. And how do we analyze that? With the now, after that, we had a slightly different problem earlier in the 21st century when we were working at the time with DARPA. And the problem was that was the time where you had the first method trying to do automatic identification or automatic sorting of faces. And so what people were doing, they would try to derive similarity using algorithm between faces to find if we can identify faces that look very much like being the faces of the same person. So what was the way the data were delivered? The university participating in the challenge would, in fact, just derive a similarity matrix among a set of faces that were given them. And I don't want to go too much into the detail, but that means that we ended up now, if we wanted to evaluate the different participants or the different competitors, we just needed to be able to integrate distances. And because one university, if you want, was a distance matrix on a set of faces. We had the same thing, of course, for smell, because smell is really a case where people where most of us are very, very bad at naming, but we know if we have smelled something before, or we know if these two smells are kind of the same and so on. And after that, more recently, we moved on to the problem of looking at brains and looking at connectivity between either functional or not. And among brains, and again, we end up when we have a set of regions of interest for one person and we have between two regions of interest, something measuring their connectivity. So if you look at that, we have something that is all the same, the same structure. We have a set of data tables that look like distances. In fact, they all are either distances or they are correlation, which is the other side of a distance. And to go to the example I'm going to present today, with the other type of problem that we have is that if we try to do replication of studies where what is involved is either correlation or distance, and that brings us to the part of the talk today between, we're going to look at distance and cosine, and everything, in fact, start by a little problem that we have these days in psychology, which is the big problem of power, underpower, overpower analysis. And I hope you remember that marvelous paper of Jacob Cohen, whose title is that the Earth is round, P.05. And Cohen, who was a psychologist, was asked, in fact, to give a talk in the late part of the 20th century to the American Statistical Association. And that was his point, was that we have a problem with the way we do statistical analysis. With the P.05 is silly in a lot of cases, because on one side, it guarantees that for every 100 experiment, every 100 useless experiment, we need to expect 5 of them to be publishable. But we've got also the other side of the fact that we can have some important results that are not going to be seen just because they are underpowered, and therefore all these ones are either ignored, or worse is that because they are not found, they are going to be systematically reproduced, but and will be published only when they fall into this 5%. And that was the point of Rosenthal, who was both a social psychologist by excellence, but also a marvelous methodologist. All that is something that we've got a beautiful book recent on that. So now the big idea after all that is that what do we do when we've got interesting data? Well, the thing that is really of importance is to replicate and reproduce. And when you have standard experiment, you just go for your analysis of variance, and your colleagues will try to replicate you. They will use the same model and so on. But now we are dealing with something a bit more complex. We want to do the same thing when you deal with multivariate data analysis. So the question now is that, can we do the same type of analysis, and can we try to validate replication with multivariate methods? So that's going to be what we're going to talk about. But before, we need maybe to refresh our memory in there. So let's start with distance and correlation. So distance in general for things, and angles are for variable. And that's when you do multivariate analysis, that's always the story. Observations are the rows, and the columns are variable, and you estimate or you analyze maps that you derive for the observation. That's going to be the distance. If you close, you are very much the same, and the further away you are, the more different you are. For variable, it's tricky because it's not exactly the same thing. For variable, the story is with angle, and that meant that for variable, if the angle is small, you're very similar. You measure the same thing. If the angle is around 90 degrees, you are orthogonal, so therefore you have nothing to do with each other. But the problem now, when you are as far as possible for variable, that means you are measuring the same thing, because you have a correlation of -1 or a cosine of -1. So let's try to see what we can do that with distance matrix of covariance. And just the overview, we're going to look at distance and correlation, then we're going to refresh with MDS, multidimensional scaling, and cov-STATIS and DisTATIS, which are generalization in 3D of MDS. And we're going to illustrate that with the SUM, which is a questionnaire that we built with colleagues from Toronto on autobiographical memory. So let's go for distance and correlation now. And there, maybe we can look at an example. We go back at that idea that we were about connectivity. So we start with region of interest, and see there are. And what we're interested in the connection between that. But what we have in general are just correlation most of the time. That could be time correlation. So that could be one type of correlation we can do. But that could be behavior. So let's look at SUM, for example, and that one for SUM is a questionnaire. We're going to see it again, where we ask questions about autobiographical memory, about semantic memory, about spatial memory. And now what you can have, if you use Likert scale like we did to evaluate that, well, we can end up with correlation matrices, and there you can see blocks around the diagonal that indicates that we have 4 or 5 factors beyond that. So, but what we want from that, we would want, of course, our usual nice picture. So the idea that we have there, because it's correlation that we're looking at, we want to have a representation so that we can have a map, and the angle between these variable will be the correlation or the covariance or the cosine. And it looks like a Euclidean stuff. So here is our good Euclid. And so let's just remember the beauty of Euclid. Well, the great thing is that Euclid is, in fact, when we talk about Euclidean method in stat, we're just talking about the Pythagorean theorem, which means that it's great as soon as you square stuff, you have all these beautiful property that mean variance and inertia are natural. And we know how to minimize, to find the minimum of whatever function, because we all know how to derive x squared. Okay? And so, and there we've got also marvelous method when it's multivariate, because we've got the eigen magic that is there, but also because this problem are used in a lot of domains, that means that we have very, very good computational routine. And we can generalize all that by adding masses and weights. And now for those of us that are more into mathematical statistics, we know that if you put multivariate normal on that, well, this is paradise, even though we, in fact, very rarely have really multivariate normal. But for correlation, what does that mean there? We start with a table of something like correlation, covariance, or more generally, cosine, and we want to have a representation. We want to be able to represent that with the map. So what do? We need to transform that, and we need some eigen magic. And when I have a problem like that, I call for help, and this is the help. This is the eigen fairy. So the eigen fairy is always it's the one who can do that transformation. So if we look at the standard idea behind that, this is MDS, metric multidimensional scaling, or classical one, also called principal coordinate analysis. And the simple idea when people have that, they take the correlation and they say, let's transform that in a distance using the D1 minus R, and they go for MDS. By the way, it may not be always the best idea, and we're going to see what. But what is MDS? But MDS is has been discovered really independently by Torgerson on one side, and it depends upon the Young-Householder transformation, but it's really the work of Torgerson for psychologists, published in Psychometrica, 58. Or if you're a biologist, we're going to call that principal coordinate analysis, and that was Gower, 1962, in Biometrica. These two didn't know each other at the time. Since then, Gower and Torgerson have met, and Gower is completely in agreement that Torgerson was number one. They both very nice people, or were very nice people, so here they are. But how do we do that? So we start with a distance matrix like that. So 0 on the diagonal, symmetric, and where we've got the usual, it's all value are non-negative, and it's symmetric, and you have the triangle inequality. With that small data, you can check that by hand. And then you want to have some magic and to transform that into a map. And here in that map, let's say the distance between A and B is A, just like in the matrix, and distance between A and C is 5, just that the same way as we have in the matrix. So, but how do we do that? So when we start the idea, this is what we want to start. We want to mimic what happened when we do a PCA. PCA, we start with observation by attributes, and we derive on one side a covariance matrix, and we go for the eigen magic, and we have our map. So now from that map, or in fact from the original data, we can get the distance. So when we want to do MDS, this is what we start with now. We start with the distance, and this is where we want to go. But now there is a problem that we cannot use the direct route there. And why is that so? For those of us with a memory about linear algebra, the story is the diagonal of 0 that tell you right away that a distance matrix is not a semi-positive definite matrices. So that meant that we're going to go into a catastrophe when we try to transform that into a map directly. So the trick is that we need first to transform the distance into a covariance. Now that we have the covariance, we have no problem. We can go on the eigen magic. So that's the little trick. Now, the trick in question to transform it is just to do, we need to do two things. We have that, first we have that diagonal that creates a problem. And then we have, if we compare a distance to a correlation, what happens is that in a correlation, the value on the diagonal is the magnitude of that value on the diagonal. First, the diagonal, sorry, is always positive, but also that means that its magnitude is always larger or equal to all the value in the rows or the column of that diagonal element. If you want to illustrate that, means if you have a correlation matrix, you know the diagonal is 1, and it's always going to be larger than any correlation because the other correlation cannot be larger than 1. So that's the first thing. So to solve that problem, the problem of making sure that it's larger, well, if you put a minus sign, all the distance are going to be below, but we don't solve the problem of the diagonal. So to solve the problem for the diagonal, we need to trick at making sure that it's going to get higher. So we need to eliminate what we can call the effect of the rows and the effect of the columns. If you do that, it looks suspiciously like doing a nice variance table when you eliminate the main effects and you just keep the interaction. So here we are, and that's what we have. So pay attention to the trick there. So we have our minus 1/2, and then those of you who teach analysis of variance will recognize right away the interaction. And if you like the matrix approach, you can use what is called a centering matrix. Okay, so if you do that, then you transform your distance matrix and you guaranteed it will work if it's a Euclidean one, you transform it into a matrix that is a semi-positive definite matrix, so we're good. So now that we do that, we can say, let's try to analyze matrices that way. So we have something now, one way or the other, we've been able to transform our matrix in something looking like a correlation. So we can say, let's go for that straight away, but maybe it's trickier than that. So let's start with a correlation matrix. So here I've got a beautiful correlation matrix, diagonal of 1, and everything works fine. And I've got the plot matching that. So here I can see that 1 and 4 are anti-correlated, and 2 and 3, 2 and 4 are positively correlated. So it looks good for one matrix, but what if I want to analyze 2 matrices and put them together? So let's put my previous correlation matrix with another one, and I want to find if they share something. Well, what happens if I plot them together? Now, it's hard for me to find if they have anything similar or not. And why is that so? Well, it looks as if the B's are on one side, the A's are on the other side, but cannot find what is common. And the problem is that the mean are very different. So I cannot compare them because they just differ from the mean. So that means that one, it's okay. If I want to get rid of the center, I'm just going to do my double centering, but I need to pay attention to one trick. I don't need the -1 because it's already this correlation matrix. The idea there is not new. To eliminate the effect of the center, it's very clearly explained in the book of Paul Horst that you see here, which is still a marvelous book. I advise everybody to read it. With title, it's Factor Analysis of Data Matrix. And we know Horst was interested about that transformation as a way of putting together what he called ipsative measurement matrix. Ipsative is a big, frightening word, but they just mean that when something is ipsative, if the value that we've got depend upon the observation. And that meant that when you have correlation matrix or when you have measurement, in some cases of ranks, these things are ipsative because they may not generalize from one person to the other. So how do we do that? So we start with our correlation and going to do a double centering. So I've got my centered correlation, and here, so that's same transformation, except we don't do the minus. So now we've got these 2, 1 are now centered. And now I can see that both of them are comparable, and I can find that first dimension is more or less common, but that the dispersion is different on the second one. But is it enough to just center? So if I look at 2 new centered matrices now, and I'm trying to analyze them, I've got a problem here because I can see that they differ both on the dispersion, on the dimension, but also of what you can call the sphericity in there. So B seems to use dimension 2 that A does not. But we have a problem. The problem there for comparison is that the first dimension is not the same. So the trick there now is that we need to try to find a way of scaling them or normalizing them, and that's the length problem. That now, if we remember one thing there is that the length, if we do a PCA or MDS, the length of a dimension is expressed by the square root of its eigenvalue that we call the singular value and that we denote by delta. So if I look at that, I have the problem, my problem now to compare these two matrices is that they don't have the same delta one. So how can I do that? Well, I can probably normalize by just choosing that. And that if you look at that now, you realize that what I'm talking about is just like a z-score, but for matrices. Z-score, you center, you subtract the mean, and then you normalize by the standard deviation, something that has got the same unit, so that now you can compare z-score. And if you do that for a matrix, eigenvalue are the equivalent of a variance, singular value are the equivalent of standard deviation, so we can normalize that. And that way, all PCs are created equal. So in my case, now I'm going to start with the first singular value of both matrices, and to normalize them, I'm going to divide by that. And now, by the way, this is as usual with the thing I'm doing. There is nothing new in that ID, and that ID, in fact, originally comes from Brigitte Escoffier and was the ID, and is the ID behind the method that her and Jérôme Pagès created now quite some time ago under the name of multiple factor analysis, which is a method used a lot, in particular now in brain imaging, but a lot in sensory evaluation and sensometrics. So now that I've normalized that, here they are, and now I can really see that the dispersion that A and B agree completely on the first dimension, but B is the only one defining the second dimension. Right. So that says that if I want to compare matrices, I need to center them and normalize them. And now, what happens if I have several correlation matrices or stuff looking like correlation matrices? And that's there that I can bring the STATIS and DisTATIS and multi-table family. So now just if you wonder what is the strange name STATIS, it's a horrible acronym. In French, from structuration des tableaux à trois indices de la statistique. And the only reason of that silly acronym was that Hervé Desplantes, who was a student of Robert Escoffier, just thought that was making a nice acronym because it was looking like the beginning of statistics, which means that if you try to find anything about STATIS, if you run a search, you are going to find tons of things about statistics. So, but in that case, what is the idea that you have a 3D matrix and you want to have two representations. You want to have a representation that would be the representation of everybody, but you want to find out the way each data table is in there. And you want also to find what is the important variable. So if we now move on to the idea of having matrices, we just have now square matrices, and we go to the same with the same idea. Now we want to have a map that tells us who is like whom in terms of what correlation matrix is like whichever one. And these one are the general family of the Procrustean analysis family, in which we're going to have DisTATIS and STATIS, generalized Procrust analysis, and so on. So let me give you a fast tour of DisTATIS. So let's look that we have 4 participants there, and we measure we use a measurement of the connectivity or correlation between the ROIs in some imaging experiment. So everybody, but we can replace that by anything that can be the way it can be a sorting matrix for wine when you've got 0, 1 representing a distance matrix or correlation. So we start with that correlation, and that if I do the analysis, I find the map below. I'm going to center and norm that, and now that one has got first dimension of 1, and it's centered, so we can compare this one. And now the first step that what we want is that I want to find something that will be the best representation. If you do PCA, they just say, oh, one column represents one variable, and I compute my component by taking a linear combination. Here I'm going to do the same thing. I'm going to take a linear combination of my matrices, and that will give me the best compromise. So for a linear combination, what I will just need to find the weights of that linear combination. So, and how can I find that? Well, to find the compromise, I need just to make my mixture, and I need just to find a set of optimal weights. If you replace matrices by columns, you can hear this is in fact PCA under another name. So, but how can I find that compromise? If you do PCA, you start by having correlation. You can do that by having a covariance, correlation, cosine matrix between the columns. We need to find the same thing in here. So, but that means we don't know what is the correlation between matrices. We need to find something equivalent, and this is the RV coefficient from Escoffier. And his paper was in 1973. Now, just for you, in French, RV coefficient is pronounced Hervé, so that means you know why I love that coefficient. So, and this is Yves Escoffier, was still with us. So, how do you compute that? So, the big thing to remember is that we deal with semi-positive definite matrices, their correlation, cosine, and covariance. First step, we vectorize that, and then we got the cross product between the two matrices, and that gives us something that is equivalent to a cross product in there. So we have now one number. Only problem with that cross product is that that cross product keeps the unit of the original matrices. So if you want to eliminate that, you can normalize by just exactly as if you were doing, in fact, a correlation where you are just going to divide them by the square root of the sum of squares. And if you do that, this is what you have, the RV coefficient. Just for those of you who want to see what is the formal approach, you can see that as being a ratio of the trace of X transpose Y divided normed by the product of the traces. Okay. And the great thing there, if you look like that, first look will tell you, oh, it looks really like a cosine. Yes, it does, but there is a little trick there. A cosine can go from -1 to +1, but because these matrices are semi-positive definite, what we have is in fact a squared cosine. So that means it will go on, take value only between 0 and 1. And that's important because that would imply something when we're going to look at the covariance correlation between participants. So here they are. I've got my 4 people. Each of them have got the normalized, standardized matrices, and I can compute the RV coefficient. Diagonal is going to be 1, but all these RV are going to be positive. What does that imply? Is that there we've got the good old Perron-Frobenius theorem. And that says that if I take the eigen decomposition of a matrix where all the numbers are non-negative, I'm guaranteed that the first eigenvector will have all the same sign. All the entries will have the same sign that we can put as being positive. So if I do that, that says that now I have what I wanted. I have a representation of the people into factorial space. But the great thing in there, they tell me that, in fact, what I have is that the larger your value, if you go back to the eigenvectors, the larger your value on the first dimension, the one where everybody loads on with the same sign, is in fact a measure of your overall similarity to everybody. You can get that because the eigenvector is very close to being an eigenvector of 1, ideally, and that will say that, oh, what you have is in fact something very close to an average of the value that you have. And so that meant that the stronger your similarity to everybody else, the larger your value. So here we can have that we see that we order our participant on what you can call the overall similarity. So that means that if I look at my weights there, I've got the ideal weights to create the ideal compromise, because they tell me that I'm going to give more weight, more importance to people who already are looking like everybody else. I accept to integrate people that are far away, but I will give them a smaller weight. So, and now when I've got that, I've got my values. I'm going to multiply everybody by my weight, and that will give me a new matrix, which is the compromise. So that means that one is the best linear combination I can find that is at the minimum square distance in the RV sense to everybody. If you remember that, then you realize what we use is just the same idea as a plain PCA. we just using, however, matrices instead of columns. And that tells us something, is that the set of semi-positive matrices is a vector space, exactly like the set of the columns of a matrix. So now what we've got is that we know how compromise is maximize that. And just like a standard of the things, we can use the, whoops. So with that, now we create our compromise S plus, and from that, we can do a PCA, and that will give us that one. I used the note slide with beer. So, but anyways, in that case, what we have is that we have the object that everybody was evaluating. In that case, that would be RI in the brain. But also what we can do, because all these matrices are semi-positive definite, we can project every matrix in the common space. And we can do that for everybody. So now that means we have a space where we can put the everybody, but we can put also the common space. Now, we have the problem when we have that, that if we want to find if the space is stable or not. So we could do a lot of things. We can, but here the trick is that we need to find stability. And one of the way of doing that will be to try to derive confidence interval. Trick is to use one of the, probably a major invention in statistics of the second part of the 20th century. It's of course the bootstrap by Efron. And that's the bootstrap in question. So, but how do we do that? So we're just going to do resampling with replacement. So that means we're going to suppose that the data we have are the best representative of a population. And if we were to sample from a population, the infinite population, probability never change. The probability distribution is fixed and cannot change in an infinite population. So we need to keep that by creating fake sample that are going to come from our sample, but with replacement. So I've got a small illustration there. So I'm put that in there, and I take and I put back that one, I copy, and I do that, and I do that, and I do that, I do that, I do that. So that what I have in here is a bootstrap sample. And from that, I'm going to repeat over and over, and I'm going to project my bootstrap there in the same space. And with that, I can have confidence interval. The idea there is that I can trust the position, the relative position of 2 points if they don't intersect, if the confidence interval do not intersect. If they do, that means that one can go into the space of the other one. If you don't like this one, or you prefer, you like a p.05, you can compute bootstrap ratios that are just like t-test, but computed from the distribution. So let's go now to the example I wanted to show you. So some years ago, almost 20 years ago, 15 years ago, we published a survey of a questionnaire that was targeted toward autobiographical memory, because we wanted to be able to find out if these individual differences would correlate with some other things. So we started with a set of questions, with 8 questions for episodic memory, what happens in life, semantic, your knowledge, spatial, your memory for places, and we had also a question about the memory for the future, which may seem strange for those of you who are unaware of the work done on psychology of memory. In fact, the idea is that a lot of memory is tailored not to remember the past, but to be able to predict what will happen. So those are the type of questions that we had. So like when I remember event, I have a hard time determining the order, or I'm highly confident in my abilities to remember past events. All that is episodic memory. Semantic is what we know. So some of the questions need to be reversed, but so I'm very good at remembering information about people that I know. Spatial, so example, my ability to navigate is better than most of my family and friends. It's not my case, I can tell you. And future, it's explicitly about the future. When I imagine an event in the future, I can picture the image and so on. So we did first then the analysis with multiple correspondence analysis, but this and we had this factor, but we just realized that when people were replicating, they were easily lost with multiple correspondence analysis. So we just decided to redo the analysis using just plain PCA. But because it's a Likert scale, when people answer from 1 to 7, it's a centered but non-normalized PCA, so that a question with a large variance should have more importance than a question with a small variance. And we did also some rotation because some colleagues really love that. So let's look at an example in here that we've got there from a paper recently published. And if you get that, so what we've got, we have, you can see you have our standard script, whoops, and we have our first dimension on which we see the future loading very clearly, second dimension being the spatial. And now the question is that we wanted to find out if that pattern was a stable pattern. So we got 31 other data set that were obtained, most of them by colleagues from other labs who were using the questionnaire. And what we wanted to know, I wanted to know if the result that we've got were stable and replicable in the centered web. So, and we had the problem of choosing the option. So I don't know if you remember the standard approach in PCA. If you want to know the number or to choose your number, you just say, let's take the eigenvalue that are larger than average, which is often thought that it should be larger than 1, but it's that one is only when you normalize everything. So we got in one of our big replication, 25,000 participants. And so the question was that should we normalize, should we do simple or double centering, and should we do varimax or not? So let's look at what we have if we do on our big set. We did the analysis, and so that's the plain covariance, and that what we were looking at. Now that's factor 3 and 4. So what we got, what we wanted in there. First dimension, you have future episodic, and second dimension is really the spatial. And then, however, when we look at the third and the fourth factor, now we have the block are well separated, but we have the hint that you have two subgroup in semantic. Now, correlation will roughly give us the same thing. So now we start with a plain covariance plus varimax, what Kaiser called the little jiffy. So it means look at everything that is keep only the dimension whose eigenvalue is larger than average, and do your rotation, your varimax rotation in there. So same thing. Now we've got a cleaner stuff. The variable are easier to interpret, but not probably that will be happier because the varimax is trying to give us a simple structure, but the idea that maybe we'll be happier if we have really a cleaner structure there, like if you were to load on one and only one dimension. So from that, we conclude that keep the covariance and varimax help us. So then I will explore the idea of the centering or double centering of the matrix. So here we go. That's our double centered matrix. It's just making clear the structure in terms of blocks that we've got in there. And if I double center the scree, if I go, that's probably 5 dimension. And then we've double centered now and not very maxed. And we find just doing that, in fact, makes our life easy. And that's probably because the first dimension, like in so many of these questionnaire, is a biased dimension when we all tend to say yes in anything concerning the same domain, in that case, memory. So from that, we conclude that we're going to keep the double centering. So now we can go to the analysis, and just in that case, oops, what do we have in this analysis? Well, we have our 31. Oops, what's going on there? so we have our 31 analysis, so one row and one column represent one analysis, and what we have measured between that is the RV coefficient between the structure that we get between the correlation, the covariance, matrix. What the first thing that we've got, which is quite good to see, is that most of the value are pretty high. But also, you are going to find, and it's not really surprising, that the ends behind these studies vary widely. The bigger study is more than 20,000, and the smaller study, in some cases, is not even 100. So we expect that the small small sample are going to be more variable, basic stat, and that's indeed what we will find. But we still have our first dimension, so that's the RV. And from that, we're going to derive the weight by just looking at the projection on the first dimension. And here they are. We have the alpha weights, the weight of the linear combination. And what we've got is that even though some really have got much stronger value, everything looks relatively nice. So let's look now at what we have, and we've done plain double center for the compromise versus the Varimax. What does that tell us? Well, that tells us in a way that just doing the double centering eliminate a lot of things and make the structure simple. Remember that what Varimax want. And we have, for the positive part of the first dimension, something quite clean, it's just spatial. Then if you look at the second dimension, we have future separated from episodic and future. And we're going to see that separation that we had when we were looking on the semantic, the semantic being broken in two groups. So, and I guess we can, so we can look even at if you look at the contributions, so it means the importance for each of the dimension, we start to see a nice separation. Top of that, I projected here the bootstrap-derived confidence interval, just to, and that support that idea that we've got, let's say, groups. Note for semantics, 6 is different. And let's say that if we were to redo that, we probably need to find a better question. So it's special S6. So, so let me so first, there is. I want to finish by showing you something that is fresh from the oven. Work that we've done with Ruchi Yu and Vincent Guimau. Ruchi Yu is now at KMH in Toronto. Vincent Guimau is in Institut Pasteur in Paris, and you can see the structure that we have now when we look at the compromise. Is that the interpretation would be easier if the structure was simpler. What do we mean by simple structure? The idea comes from Thurston, when he was talking about factor analysis. And for Thurston, the idea that we have a simple structure if when you look at one variable will load on one and only one or very few component, and you are going to have the converse that when you look at a component, the variable are either very high on the component or very low. Ideally, you would have 1 and 0. And so to obtain that result, what people do traditionally, that what I was mentioning, is to move toward approaches such as Varimax. But Varimax, in some cases, improves. Most of the time it does, but it still does not give exactly what we want. And it's because when you move to Varimax, you're going to try to use something like maximizing the fourth power, which indeed exaggerate the difference between being small and being big. But what we decided a few years ago, actually, when I was in Paris for a sabbatical at the Institut d'Études Avancées. So what we started to work with Vincent on the problem of trying to explicitly get a criterion to go to simple structure. And what we realized indeed that some work had already been done, but the work that then was done was losing something, was making to get there. So most of the time when you were using a lasso approach, which means that you try to explicitly force the number of zeros, the problem that we have when we do that is that lasso loses something of interest, which is orthogonality, that we like to have orthogonal dimension because when we interpret one dimension, we don't have to interpret the other. In terms of psychology, having an orthogonal dimension means that we are dealing with phenomena that are uncorrelated with each other. And that means that they correspond to independent structures in there. So we decided to work on that, on trying to develop a new approach for specifying, including the standard approach, having the larger, forcing the value towards 0 or making big, but we wanted to keep orthogonality. Just barely 10 years after, I'm trying to say, we continued there and we decided to work that on STATIS and DisTATIS. There we found that we have two ways of specifying. We can either specify at the level of the RV matrix, so that means either you there or you not, or we could specify at the level of the compromise. So let's look at what the script for plain statis. So when we are not sparse, we can see we have indication that first dimension is clean, second is clean, and 3 and 4 are spherical, so that we want to keep that. So that one was the RV map in there. So when we look at that RV map, we have what we expect, a very strong first dimension. And after that, we had to find out a lot of the value for the parameters to improve our search, and we needed to decide about the number of components. So we found here the optimum was 4 solutions. And when we specify here, we have representing the loadings for each of the dimensions, you can see that if you look at each of our subcomponents, either they load or they do not load. If I put, it's clear if I put that as a map. Now we isolate very clearly a first dimension that is pure spatial. Second dimension is pure semantic. Third dimension is pure future. And episodic is loading on in there, but we'll see it later on. So we can also specify only the RV, but not specifying the compromise if we want to. And there we end up with 3 dimensions in there. And the main interest that we have is that it tells us that the sample size is really important, because this is what separates the type of studies. So let me, I think that we are now getting close to our 45 minutes. So I think it's time to wrap it up. So what was the idea in there? What I presented you was a method that is very much in the spirit of PCA. So it means we try to have a representation that maximizes a square correlation or square cosine in our case. And the only difference, or the main difference between this approach that is going to use either distance or cosine matrices compared to PCA, it's just that we are integrating these matrices into one compromise, but contrary to plain PCA, we have 2 maps. We have one map that telling us what matrix is looking like what other matrices, and from that map we can derive a coefficient that allows us to have an optimum representation for all these matrices by another matrix that can be decomposed as a map. And in the recent development, we found a way of trying to make the interpretation easier by forcing the structure of the representation to be simple. And I think that I've gone through what I wanted to share with you.
Okay, so a very exciting talk. Thank you very much.
Thank you.
Let move to the audience, and maybe there are a few questions that the can you stop sharing your
Oh, absolutely. That's absolutely yeah.
Okay, excellent. So let me start with the first question. So so my question is about the difference between the statis and multiple factorial analysis.
Mhm.
It seems like I know. So the difference is based on the normalization.
Yeah, it's very small.
Yeah, it's very small. The difference is how we normalize the different tables, and so in statis, the normalization comes from the only the first eigenvector of the compromise, and with Brigitte Escoffier and Jérôme Pagès, they're normalized by the trace of the whole compromise. So is that right? And have you
By the trace is some PCA that
yes
yeah,
the trace of the PCA. So from the practical point of view, have you because you are using both of them, so what do you think about which normalization suits to you the best?
In practice, I found that at least for most of the examples that we used, that both normalization are worth having together. That being said, when you look at the, if you have done your MFA or some PCA, in fact, normalization, most of the time what happens, you find that your alpha weights are very similar. Okay. So that meant that the either first singular value or trace normalization equalize the variance in such a way that you don't have very, very big differences. And there is one thing in terms of norm that is also in the, I've forgotten also to say that we have an R package that you can get from the Crown for my homepage if you want to have the last version, where all these options are part of the program. So you can decide if you want MFA normalization or some PCA normalization, or even a third one if you want to have the nuclear norm, which is the sum of the singular value. And so we've got all that in there.
Okay, and my second question, and I'm going to let the other people ask me a question too. My second question concerns the sparsification. See, this is your last slide.
Yeah.
And
that, and I'm happy that Vincent is here, so I'll be able to delegate all the questions, because it's really Vincent and Ruchi that are really the main. They are, the leaders there.
So it seems that the component that you got are, of course, they are orthogonal, but it seems more related to what we expect. I mean, from the data sets. So I'm just wondering about the if we do like statis, the compromise, and rather than working with the orthogonality of the component, we introduce some criterion like independency. I'm thinking about ICA.
Yeah, I can see if you say independent, I see behind it's written ICA.
Exactly. So having the compromise, then looking at the independent component. So I'm just wondering what is the relationship with this specification, and probably changing the criterion, looking at the independency rather than the variance.
Yeah, and then I'm forced to tell you I've got no clue.
Okay.
Because I think the problem, if we try when we specify that the problem of the way we treat project onto a subspace in there, and then the way we were able to try to find out, because at first, Vincent tell me if my memory is vacillating on that, but I remember at first we were just trying to get the orthogonality as being almost like an explicit constraint. And this is there that we suffered, and we try, we got lost in a proximal operators. I don't know. We had a good time, but we would. So the problem, to get back to that to integrate the constraint of ICA, I don't think it's going to be completely obvious to me. Vincent, what do you think?
Exactly what you said. We need a projection operator for our method to work, and I'm not sure that we could get it that would emulate the independence of components. I wouldn't know how to do that yet, but this is a very interesting question. I would be very excited to procrastinate on that.
But maybe we can find a tricky that we can get out with an assumption. Because if we assume but I'm not totally convinced it is the case.
Especially not in the sum space.
No, in fact, I'm not sure that I've ever analyzed data except simulated data that were multivariate.
Oh yeah, it works when we simulate data.
If you simulate data, it works. Habib, I'm sorry, I'm not sure that we answer your question.
No. No, you answered the question because you are mainly based on the projecting the data and project curves. So and if we apply the ICA technique, this is not a projection. And so it's labeled quite different, but we can maybe we can merge between the STATIS technique and the ICA technique at where the compromise is projected on independent component rather than orthogonal.
Oh, okay, yeah.
So that's something we can probably do. So injecting something more specific, but we can talk about this. It's a more technical aspect. So anyway, any question from the audience? No. Yes.
I'm looking also in the sky.
Okay. So I have a general question for you again. My question is, okay, rather than having different matrices of different similarities, my question is, if we have a different graph, let's say I am looking to the brain activity and I am following the brain activity, and each step I can extract a graph looking at the connectivity area of the brain. So, and I would like to study the similarity between matrices, and this is the between functional connectivity matrices. So the graph is a specific structures. So how you think we can apply the DisTATIS technique or generalized technique to this kind of graphs? So it's DisTATIS for graph.
Yeah. So and you're just thinking about the connectivity. That means we just have 0, 1s.
Oh yeah.
Or do you want to have a correlation, time correlation?
So let's say both. So if we look at the anatomical connectivity, we can simplify this and say, okay, area, it's like a structure of a graph, 0 and 1. So area who are connected and area who are not connected from the anatomical point of view, or we can weight by the diffusion imaging. So this is another aspect.
What we're also working on with Vincent and Ruchi and a couple of colleagues. But I think if we look at the connectivity matrix, the 0, 1s, you have two cases. You have the nice case where the connectivity is symmetric.
Yes.
So if the connectivity is symmetric, that's completely straightforward because your matrix, if you just load the diagonal, is semi-positive definite. So you push the button, it will work. Now the trick is that if they're not symmetric, then there is something horrible we will have to think, and I really don't like that. if we don't want to do that. But I think it's the probably trick, which would be, and that would be a fun project, in fact, there would be to get back to the problem of integrating now matrices that are by definition non-semi-positive definitive. They're not symmetric, they're not. So the trick will be either to cheat by creating the symmetric and matrices for the analysis and desymmetricize it at some point. I can see that Vincent is absolutely not for that. Or the thing is to find the equivalent of the RV coefficient.
Yeah, so this is really
that's just the trick. You just need to find something that has the property of the RV coefficient between non-symmetric, because you bring the symmetry of the matrix only when you want to analyze the compromise. So that would mean you end up with a matrix that will be just like a confusion matrix. No, when you aggregate all your matrices, you would have something like a confusion matrix that you can probably analyze by something you know very well, Habib, because that would be something you can probably analyze via correspondence analysis.
Okay. Okay, we can talk about.
We can talk about it, but I think that's something we need to pursue, and because that in terms of aggregating, the key point is find something equivalent to the RV.
Yes. So my understanding now is that because we have both cases. In one case, this is one work that Arsalan, who is a researcher he's developing a model to look at the propagation of the topology within the brain. This is in Alzheimer's.
It's Alzheimer's stuff, right?
Okay, and and we know that this propagation goes through the axons. So one of the things is that the axon, we can get some information from the connectivity, the anatomical connectivity area, looking at the diffusion imaging. And this is some information that we have. Now the question is, is the diffusion of the topology within the brain is symmetric? And the response is no. This is not non-symmetric. So when we got
that makes sense.
Topology within the brain, so it means that the diffusion from A to B is different from the diffusion from B to A. So the connectivity is not symmetric. So in this case, how we can model this? If we would like to follow this process, looking at the technique that you are proposing, all the techniques suppose the symmetry and extract some information based on this kind of symmetry. If now we don't have the symmetry, how we can generalize this? So what you are saying is that I agree. We are looking at the Hervé, and we can generalize the Hervé coefficient in a non-symmetric graph. So this is something who can be applied. So we can try to look at the compromise with a non-symmetric measure. So that's something that's my understanding of your.
That's exactly that.
Okay. That's
another line of approach would be things that we talked about several years ago. I don't know if you remember when we're just thinking about working on the Laplacian instead of working on the connectivity and so on.
Yes, absolutely. So I'm pushing this area. So rather than looking at the similarity on the graph, we replace the graph by the Laplacian operator. So now we have different Laplacian operators. So we have different operator, and we would like to have the compromise between different operator. So it's like a generalization of what we did within the STATIS approach. It's still a STATIS spirit, looking at eigendecomposition of operator, but this helped us to solve the problem of this double centering the data set. And with the graph, the Laplacian operator is semi-definite matrix. So this is something that we can apply with.
As long as we semi-definite way, semi-positive definite way.
That's worked very well. So we have some yeah, we apply this to our graph. So maybe we can talk about this a little bit later, because
yeah,
we move from the similarity, we extract the Laplacian operator, we look at the eigen vectors of the Laplacian operator. So the eigenvectors become...
You have seen our eigenfairy, isn't she adorable?
Yeah. And we extract those matrices, and then we apply the STATIS technique. So we enter the STATIS technique after extracting the eigen decomposition.
The eigen, yeah.
Yeah. So that's something we are applying right now, and this is something that we are going to discuss. Obai, who is online, he did some work in this area, and he is going to show us also.
Oh, great!
What he got using Laplacian operator. Okay. Still, any other question, Hervé?
I have, excuse me.
Yes.
Oh, go ahead.
Yeah, so I have one comment regarding the current discussion that we are having. So like I was following another work of Professor Ramamurthy, and also what he does is that he started to prove all these things like the counterpart of this Penrose Frobenius theorem and all this in this non-symmetric graph. So generally the problem arises when we have different coefficient of transition. So like he did some work regarding the diameter and eccentricity of the graph and regarding this. And also what he was trying to do is like he was also analyzing kind of similar method, but he was building having a connectivity matrix, and out of that they are building a Markov chain. So essentially it is kind of how the information is flowing through the brain. So they were building a Markov chain model, and after that they were looking at the stationary distribution to identify the key hubs of this Markov chain. And in this particular work, he showed that this method still works for if we take like non-symmetric matrices. So like regarding this discussion, I think we can follow some of his work to like develop the method towards non-symmetric matrices. I believe. I'm not quite sure like how the technicalities will form later, but like there is some suggestion.
But it looks that it's worth trying at least.
Yeah. So thank you, Sorin.
Great.
For this. Any other question? Okay, guys. If there is no questions, so we are going to close this session with the talk of Hervé.